Bismillahirrahmanirrahim. Assalamualaikum students. So far we have studied combinational logic circuits, um, and in this chapter we will start the study of the fundamental of the sequential logic circuits. And there are different types of sequential logic circuits. Bistable multi-vibrator devices are also discussed in ongoing chapters. Uh, from the two categories of the bistable devices, includes latches and the flip-flops. Besides, these devices have two stable states called set and reset states. They can retain either of these states indefinitely, making them useful as storage devices. The basic difference between latches and flip-flops is the way in which they are changed from one state to other. So their details will be covered in the next chapters. And here in this lecture, we will talk about the synchronous sequential logic circuits. As we can say that every digital system is likely to have combination circuits, and most of the systems encountered in practice also include storage elements which require that the system be described in terms of sequential logic circuits. And we can see a block diagram of a sequential circuit, and it consists of combinational logic circuits, and along with the combination logic circuits, there is also uh, a memory and element is included, which is also used as a feedback path from the output of the combination circuit to the input. And by using these uh, memory elements, we can store different types of data in the, we can say, digital circuits, and store them the data. The sequential circuits receives binary information from external inputs, and together with the present state of the storage element determine the binary value of the outputs. These external inputs also determine the condition for changing the state in the storage element. The block diagram which we can see in this figure, it shows us that the outputs in a sequential circuits are a function not only that of the inputs but also a function of the, you can say, the present state of the storage element. And we can say next state of the storage element is also a function of external inputs and the present state of the storage element. So sequential circuit is specified by a time sequence of inputs, outputs, and internal states. In contrast with the output of the combinational logic depends only on the present value of the sequential circuit. As we know that in combination logic circuits, the output of combination logic circuits only depends upon the present state of the inputs. But in sequential circuits, the output depends on the present state of the input and the previous states of the memory elements. And so far, as we can say, there are two main types of sequential circuits, and depend upon the function of the timing of their signals. And from these two types of sequential circuits, one of them is a synchronous sequential circuit, and the other is asynchronous sequential circuits. Sequential circuits also, we can say, may use flip-flops to store as many bits as necessary, and the outputs from these things can become either from the combination circuit or from the flip-flops or both. As we can see in this block diagram, that output can become from the combination circuit or from the flip-flops, and flip-flops also includes clock pulses which are used to enable the sequential circuits or flip-flops. if we consider these, we can say now flip-flop, the storage memory is used in, you can say, clock sequential circuits. The storage elements used in clock sequential circuits are called flip-flops. A flip-flop is a binary storage device capable of storing one bit of the information at a time. In a stable state, the output of a flip-flop is either 0 or 1. A sequential circuit may use many flip-flops to store as many bits as necessary. The block diagram of synchronous clock sequential circuit, as is shown in this figure, you can see. And the outputs are formed by combination logic function of the inputs to the circuit of the or the values stored in the flip-flops are both. The value that is stored in a flip-flop when the clock pulse occurs is also determined by the inputs to the circuit or the values presently stored in the flip-flop. The new value is stored, that is flip-flop is updated when a pulse of the clock signal occurs. We can say when the pulse of the clock signal will be occurred, then the value which is present in the flip-flop or stored in the flip-flop will be updated at the occurrence of each pulse of the clock signal, which is also clock pulse, which is also the input of the flip-flop. So the new values which are stored in the flip-flop are we can say updated when a pulse of the clock signal occurs. And prior to the occurrence of the clock pulse, the combinational logic, forming the next value of the flip-flop must have reached a stable state or stable value. Consequently, the speed at which the combination logic circuit operates is critical, and if the clock pulses arise at a regular interval, as you can see in this figure that clock pulses are occurring at a regular interval of time, the combination logic must respond to a change in the state of the flip-flop in time to be updated before the next pulse arrives. And we can say there is a type of propagation delay also plays an important role in determining the next state and the minimum interval between clock pulses that will allow the circuit to operate correctly. The state of the flip-flops can change only during a clock pulse transition. The state of the, we can say, flip-flop can only during the clock pulse transition. Transition means when clock pulse changes from a zero state to the uh, high or one state, then the changes will be occurred during a clock pulse transition. For example, we can explain this when the value of the clock signal changes from 0 to 1, or when clock pulse is not active and it changes from not active to active state, the feedback loop between the value stored in the flip-flop and value formed at the input to the flip-flop is effectively broken because the flip-flop outputs cannot change even if the outputs of the combination circuit driving their inputs change in value. Thus, we can say the state of the, or we can say state of the flip-flop or the output of the flip-flop will be updated or will be changed during the transition period of the clock pulse. And the transition from one state to the next occurs only at the predetermined interval dictated by the clock pulse. These clock pulses plays an important role in the transition of the, we can say, these synchronous clock sequential circuits. Latches, and we can say these are also a type of storage elements, and we use in more different, we can say, digital circuits. The SR latch is a circuit with two cross-coupled NOR gates, or we can say two cross-coupled NAND gates can also be used, and it has two input labeled S for the set state and R for the reset state, and similarly it has two outputs, uh, which we can say that the Q and the complement of the Q. which are both outputs are complement of each other. And in a storage, we can say element in a digital circuit can maintain a binary state indefinitely as long as power is delivered to the circuit until directed by an input signal to switch the states of the storage elements, are we can say the major differences among various types of storage elements are in the number of inputs they possess and in the manner in which the inputs affect the binary state of the storage elements that operate with signal levels, or we can say that with the clock signal rather than signal transitions are referred to as latches. Those controlled by a clock transition are said to be flip-flops. Latches are said to be level sensitive devices, and flip flops are edge sensitive devices. The difference between latches and flip flops, we can uh, say that latches are, we can say latches are edge level sensitive devices. As we are going to study SR latch, and latches are level sensitive devices, and the flip flops, which will be discussed in the next topics, are clock, we can say the edge sensitive devices. The two types of storage elements are related because latches are the binary information are basic circuits from latches are basic circuits from which the flip flops are constructed, and although latches are useful for storing binary information and for the design of asynchronous sequential circuits, which will be discussed in more detail in the next chapters of in this book. And we can say they are not practical for use in synchronous sequential circuits because they are building blocks of flip-flops. However, we will consider fundamental storage mechanism used in latches before considering flip-flops, as we will discuss these flip-flops in the next lecture. In this lecture, we will focus on the latches and their function and their applicability and how they work. As we can say, the SR latch have with the, we can um, develop these SR latches by using either NOR gate or by using with the help of NAND gates. As we can see in this diagram, NAND gates are used to develop a sequential circuit of SR latches. And in previous figure, we can see that NOR gates are used to develop the SR latches. SR latch is a circuit with, as we can see, with two NOR gates which are cross coupled. And in next figure, we have also seen that we can use NAND gates. And here S, both two inputs of these latches, one is S and one is R. S is for set state and R is for the reset state. And mm, when we are going to explain these latches, the latch has two useful states. When output Q is 1, we can see in this truth table, when output Q is 1, the output Q complement is 0. The latch is said to be in the set state. So we can say that the outputs of these latches define the state of the latches, and it says that when output Q is 1 and bar or Q prime is 0, the latch is said to be in the set state. And when Q is 0 and Q prime is 1, then latch is said to be it is in the reset state. And outputs Q and Q are normally the complement of each other. So when both inputs are equal to 1 at the same time, at that state, uh, there is a condition which occurs in which the both the outputs are also equal to 0 rather than be the mutually complementary forms. Those are not complements to each other. As we can say that in this state, when both the inputs are 1 1, these output states are, you can say, are 0 0. If both inputs are then switched to uh, 0 simultaneously, the device will enter an unpredictable or undefined state, or we can say a metastable state. Consequently, in practical applications, setting both inputs to 1 is, we can say, is a forbidden, that we will not consider these two states when both the inputs are set to be 1. Both inputs, when both inputs are set to the 1, this state is, we can say, is the forbidden state. And under normal conditions, both inputs of the latch remain at 0 unless the state has to be changed. That both the inputs will be remain at 0 until and unless the state has to be changed. And we can say when the input s is 0 and r is also equal to 0, so then we can see that in a NOR gate, the output, as we can see, that will be dependent upon the values of the inputs. And the application of a momentary 1 to the, when both the inputs are 0, and we will change the inputs when we have to change the state. And so the s input must go in the the application of a momentary 1 to the s input causes the latch to go to the set state. When we changes s from 0 to 1, it changes the system from reset to set state to take place. As we can see that if s is 1 and r is 0, then in that case the s input will be changed in order from, so we can use annotation here. And according to that, if we can see that s is equal to 1 and r is equal to 0, and in that case we will check that what will be the output of the system. And in that case we will see that as for the case when s is equal to 1, then previously at the uh, point when both the inputs are 0 0, the output is in the state of 0 and 1, as q is equal to 0 and q prime is equal to 1 when both the inputs are 0 0. And when we changes the s set state from 0 to 1, the output will be changed, as we can see from here. When both the inputs are 0 0, the outputs are 0 and 1. So here is also a 0, and at this stage there is a 1. And so when we changes the set state from 0 to 1, here it will be 1, and at this input this is already a 0. So in OR gate, in case of an OR gate, the output will be equal to 0, as in the case of an OR gate, when two inputs are different, the output is equal to a 0. So this 0 will be directed to this point, and when both at reset state is already at the state of 0, when both inputs are 0, so the output will be become 1, and the state will be changed from the 0 1 to 1 0, and which is known as the set state of the latch. And it will remain 1 0 when we again changes in the states from 10 to 00, it will remain 10 until and unless we have changed the sets state from 0 to sorry, from 1 to 0. And when we will change s from 1 to 0, the output will be changed from 0 to 1, and it will become a reset state, and the latch will be in the reset state. So these conditions we use here are to set the states of latches in set and reset states. The SR latches, we can say we can also uh, develop by using NAND gates, as we can see in the next slide. SR latch with the use of NAND gate. The two NAND gates are cross coupled, as we can see in this diagram. It operates with both inputs normally at 1 unless the state of the latch has to be changed. As we have seen in the previous state, when both the NOR gates were cross coupled, then state has, when both the state inputs are at 0, then that there was the state of, we can say, we have to change the set state from 0 to 1 to change the state of the latch. But in the case of SR latch with NAND gates, we both inputs normally remain at 1 unless the state of the latch has to be changed. And we can say when the application of 0 to the set input, or we can say the S input, causes the output Q to go to 1, putting the latch in the set state. And when the S input go back to 1, the circuit remains in the set state after both inputs go back to the 1, as we can see in this table, that when both the inputs are 1 1, the system or the latch remains in the state at which was previously. And when we change the value, we can say from 1 to 0, then the state of the system changes, as we can see in this truth table. So let me explain you by using these annotations. When both the inputs are 1 and 1, the system will be in the state in which it is previously happened. We can see it has states of as 1 and 0. Output is Q is also 1 and Q prime 0. And when we change the input from 1 1 to 1 0, S is equal to 1 and R is equal to 0, then the output will be changed from 1 0 to 0 1, as in the case of NAND gate. When these both inputs are 1 1, the output will be equal to 0, and this 0 will cause this input change to 0, and the output will be go to high state. And so the state of the latch will be changed from 1 0 to 0 1, and it will remain in this state until and unless if both the inputs are 1 1, it will be remain in the state of, we can say, set state 0 1, and it will be changed when we change the value of S from 1 to 0, and when it goes from 1 to 0, 1 1 to 0 1, and it will go to 1 0 state, which is a reset state of the system. And so in this the condition that is forbidden for the NAND latch is when both the inputs are being equal to 0, and so that condition will be a forbidden state of the NAND gate, and we, we would do our best to avoid this state of when both inputs are 0 0, or when both are 1 1 in case of NOR gates. And so when we in comparing both the NAND and NOR latch, note that input signal for the NAND requires a complement of those values used for the NOR latch. Because NAND latch requires a zero signal to change its state, and it is sometimes referred to as an S prime or prime latch. The primes are sometimes bars over the letters, designate the fact that the inputs must be in their complement form to activate the circuit. We have to, when we have to activate a circuit, we will use this system. So these are the SR latch by using an AND and NOR gates. Uh, so the basic operation of the SR latch can be modified by using a control signal or a control additional input signal, which determines that whether the SR latch has to be changed its state or not. An SR latch with a control input, which we can see in this logic diagram. And this C here shows the control signal. We can also use E and EN signal, which we can say enable input to enable or disable the circuit. So in the we can say the base SR latch with a control input can additional is implemented by using NAND gates, and it has two additional NAND gates which are used more than the NAND gates which are cross coupled with each other. Additional two NAND gates are used. The control input EN acts as an enable signal for the other two inputs, and the outputs of the NAND gates, we can say the output NAND gates stay at logic 1 level as long as the enable input is equal to 0. So until and unless the enable signal is changed, if enable is equal to or control signal is equal to 0, the state of the system cannot be changed, and the control input as which acts as a control input signal, it has to be one to change the state of the system. The outputs of the NAND gates stay at logic 1 level as long as enable signal remains at 0, and this is the quiescent condition for the SR latch. When the enable input goes from 0 to 1, it will allow in the SR latch to change its states. And when enable input goes to 1, information from the S or R input is allowed to affect the latch. The set state is reached with S is equal to 1 and R is equal to 0, and enable input or control input is equal to 1. When S is equal to 1 and R is equal to 0 and enable equal to 1 to change the state of the SR latch to the set state. To change the set state to the reset state, the inputs must be S is equal to 0 and R equal to 1, and enable must be equal to 1 in that case to change the state from the set state to the reset state. In either case, when enable returns to 0, the circuit will remain in the state of in previous state, in the current will, or we can say in the current state. The control input disables the circuit by applying 0 to the enable signal or the control input, so that the state of the output does not change regardless of the values of s and r, and that how many times we will change the value of s and r until and unless if the value of enable input or control input is 0, the output uh, of q and q will not be changed until and unless the value of the enable signal goes from 0 to 1. When enable is equal to 1 and both S and R inputs are equal to 0, the state of the circuit does not change either. When enable is 1 and S and R both are 1, I just can write down here 1, and S is 0 and R is also 0, then the we can say the state of the circuit will not be changed, and we can say these states conditions are listed in function table accompanying the diagram we have stated. These states will, I can say, no change will be occurred. When no change will occur when the control input or enable input is 0, or when both the S and R are equal to 0. In these conditions, no change will be occurred at the output of the SR latches. And when we change the value of control signal from 0 to 1, the states will be started to change, and by changing the values of S and R. And third, the other state we can say that indeterminate condition occurs when all the three inputs are equal to 1, as we can see in this table. This is known as indeterminate condition. This condition places zeros on both the inputs of the basic SR latch, which puts it in an undefined state. When enable input goes back to 0, one cannot conclusively determine the next state because it depends on whether the S or R input goes to 0 first. So the indeterminate condition makes this circuit difficult to manage, and it is seldom used in practice. So we have to avoid these combination of the inputs when we are going to apply our in the practical of our labs. So it is an important circuit because other useful latches and flip-flops are constructed by using these SR latches. So inshallah, in our next lecture, we will see about the D latch, which is also known as a transparent latch, and by using that we will see that how we will implement that transparent latch and what are the functions and how it operates. So inshallah, this will take care. Allah Hafiz.